As we all know, life has existed on the planet for 4 billion years. However, it could have occurred shortly after the Big Bang, when the universe was more fantastic than it is today. A universe that may have been favorable for life to develop in different places. It is possible that there are dormant seeds of life in the cosmos waiting for the right conditions to flourish, regardless of their size. Extraterrestrial life may be widespread. In this video, we will explore two speculative but scientifically valid scenarios. To provide a comprehensive explanation, let's begin with the Earth's life paradox. During its initial several hundred million years, Earth endured extreme conditions, including asteroid impacts and a molten surface. However, once the first oceans formed, life swiftly emerged, with countless microbes colonizing every available space. This phenomenon is quite peculiar. It seems as though life on Earth has existed almost as long as the planet itself, almost as if it was patiently awaiting an opportunity. What's even more remarkable is that life didn't just emerge rapidly within this brief time frame. It also traversed a substantial evolutionary leap. Even microorganisms, which are the simplest living organisms, require the ability to eat, grow, and reproduce. To accomplish these tasks, they necessitate a functioning genome. The mystery is how organisms without a genome have evolved to life. The existence of a genome is one of the most puzzling mysteries in science. If we greatly simplify the question, it boils down to a riddle. In order to have a functional genome, you need proteins, and in order to make proteins, you need a functional genome. Both proteins and genomes are complex, extended molecules built from intricate components that are extremely difficult to assemble randomly. This predicament is reminiscent of the endless cycle of chicken and egg scenarios. Once a complete structure appears in a cell, the whole system works smoothly. However, if one were to start with elementary non-living matter and reach that level of complexity through random chance alone, it would require an enormous amount of time for trial and error. So how were the original living organisms able to bridge this gap in just a few 100 million years? Most theories of the origin of life attempt to fill this gap by proposing mechanisms for the efficient emergence of the first self-reproducing organisms from a primordial soup of prebiotic molecules. However, we still do not have a precise idea of how this process might have functioned. Perhaps we need the opposite approach. The clock of evolution. Think of genomes as the historical narrative of life. As time passed and life evolved, new characters emerged. From amoebas to fish, amphibians, dinosaurs, and mammals. Over billions of years, the narrative of life became increasingly convoluted. The genome can be thought of as a long sequence of letters containing biological instructions. And it appears that from microbes to modern humans, functional genomes have increased in size at a relatively constant rate. Fish have more than twice as large a functional genome as worms, and our functional genome is about twice as large as fish. This pattern suggests that genomes are doubling on average every 350 million years, as if evolution is running on an exponential clock. Even more intriguing is the fact that the earliest terrestrial microbes, despite their simplicity, had remarkably long and complex genomes. How life was able to achieve such complexity in a relatively short period of time remains an interesting mystery. Extrapolating our exponential clock back to the simplest conceivable life form with a genome, we arrive at a time frame of 10 billion years in the past, more than twice the age of the Earth. This suggests that if life evolved in this way, it did not originate on Earth, but most likely somewhere in space. This may clarify why life flourished so quickly on our young planet. If it already existed in space, like a dormant seed, then all it needed to awaken and continue its evolution was water and warm temperatures. In addition, this concept helps explain the amazing sophistication of the earliest life forms on Earth, since they could have evolved over billions of years in some other corner of the universe. When we search for life in space, our focus is on Earth-like planets, situated at just the right distance from their star to maintain conditions suitable for liquid water. However, there was a time when almost the entire universe could have been habitable, shortly after the Big Bang. At that point, the universe was exceedingly hot, but as it expanded, it gradually cooled. Between approximately 10 and 17 million years after the Big Bang, when the universe was just 1,000 times younger than it is today, temperatures ranged from 100 degrees Celsius to 0 degrees Celsius, the range in which water remains a liquid. During this window of time, over 13.7 billion years ago, the entire universe, without exception, possessed the appropriate temperature to support life. However, having the right temperature alone is insufficient for life. Essential chemical elements like carbon and oxygen are required, and these elements are formed during the life cycles of stars. But did stars exist in the very early universe? The answer is possibly yes, particularly in regions where matter was densely concentrated. These early stars would have been exceptionally massive and could have gone supernova in a relatively short span of 3 million years. Perhaps the first ancestors of life were more exotic and didn't even need water, but thrived in substances like ammonia or ethane, which can remain liquid at temperatures well below 0 degrees Celsius. They could exist from the residual heat of the Big Bang for tens of millions of years, right up to the time when we know for sure that stars and all the chemical elements existed. The real magic of this idea is that although the modern universe is extremely deadly and hostile, back then the conditions for life could have been virtually everywhere for a period that could have lasted several tens of millions of years. Primordial life could have arisen on any rock, even between the stars. So in the universe came the beginnings of what would evolve billions of years later into bacteria, trilobites, dinosaurs, and finally us. As the universe gradually cooled below the temperature necessary for life to evolve, some of these ancestral life forms may have survived by finding refuge in the warmth of the first planets, hiding in frozen asteroids, or even hibernating in cosmic dust. If this were the case, life could be widespread throughout the universe. Whether we will ever get confirmation of this, however, remains unclear. Nevertheless, if life did indeed originate from space and reach Earth, then logically it should have seeded other places in our solar system as well. Fossils might exist in the arid Martian riverbeds. Potentially, life could soon be discovered in the toasty subterranean oceans of Enceladus, Europa, or Titan, where ethane and methane form seas, rivers, and lakes as warm as the universe when it was 90 million years old. Detecting alien life on Titan would bolster the notion that life might have originated in the early universe. When surveying the cosmos, we've yet to encounter any entities resembling us. This absence could be due to the necessity of life requiring 10 billion years or more to attain the complexity needed for a technological civilization. Conceivably, there are numerous planets teeming with microbes, oceans housing exotic fish, continents populated by peculiar creatures, and maybe even beings akin to us who have recently awakened to consciousness.